Good evening viewers. In this session we are going to discuss about the topic autocorrelation and heteroscedasticity. This topic pertains to the course MECE 001, particularly block 2 of the course Econometric Methods. This is a part of the MA Economics program. In econometrics particularly we have two types of situations. One is theoretical econometrics, the other is applied econometrics. In theoretical econometrics, we basically study about the design of test statistics and estimation methods. How a particular test should be conducted, how a particular equation or econometric model should be tested, that is the arena of theoretical econometrics. But in applied econometrics, we study a variety of areas where we apply the test statistics and estimation techniques to different fields. For example, in finance, in trade, in industry, or even in agriculture. So in these areas, how the test statistics designed in theoretical econometrics are applied, that is the subject matter that we study. But today's topic is quite preliminary in the view that we are going to cover some of the introductory concepts. We begin with the ordinary least squares model, or you call it OLS model, and on that basis of OLS model we move on to some of the further steps. In OLS model, as you can find out, that we have a very simple equation. It is a two variable model. There are two variables, x is the independent variable and y is the dependent variable. You can call it the x is the explanatory variable and y is the explained variable also. Beside the parameters, these two parameters alpha and beta, this gives a structure to the model in fact. Here you can see that it is a linear equation, y equals alpha plus beta xi plus epsilon I. Epsilon I in this case is the stochastic error term. Here, like it is not a deterministic relationship. In a deterministic relationship, as you know, in the case of this regression models in fact, that x solely determines y, or there is only one explanatory variable and there is nothing in between. Given the value of x, you get the value of y if the parameters alpha and beta are known. But in this case, in econometrics particularly, we have a concept of stochastic error term. So what happens that in this model, x remains fixed when you are taking so many samples. Suppose you are taking n number of samples. It could be 30, 40, 50, or hypothetically any number of samples that you take. In all the samples, the value of x remains constant. So whatever set of values that you are taking, this set of values remains unchanged. For example, suppose you are estimating the relationship between income and expenditure of certain households. So you selected suppose 100 households, and these households have a particular income, that is your xi in this case. So for the ith household, xi is the income of the household. So on the basis of that xi, the income of the household, your expenditure of the household is determined. Okay. So here xi is the independent variable or explanatory variable and yi is the dependent or the explained variable. Here epsilon I is the error term. So given this model, what we do next is we have certain assumptions underlying this model. In this linear relationship where xi is a straight line, the yi equals alpha plus beta xi plus epsilon I, the regression model that we are taking, the OLS model that we have, it is a linear model in the sense that it is a straight line relationship. When we estimate the model and plot it on a diagram, we get a straight line on the basis of the above model. There are certain underlying assumptions in this model. There are basically four assumptions. Four are quite prominent. One is that the error term has the zero expectation value. When we take expectation of epsilon, it is 0. That means that if for the whole population, if we take the relationship, in that case the expected value or the mean is coming out to be 0 for the population. Okay. For the sample also, if it is a large sample, on an average we assume that the average of epsilon is coming out to be 0. This is some assumption that we take. The second assumption that we have is that the variance of the error term, the stochastic error term that we discussed earlier, epsilon I, that is fixed, that is sigma square, that is constant throughout the model. So if we are having, suppose, 100 households in our sample, so for all 100 households the variance is fixed, it is constant, it doesn't change. This is the second assumption that we have. And a third assumption is that there is no relationship between error term in one observation and error term in another observation. We call it expectation of epsilon I, epsilon j is equal to 0. That means that the error term in the case of one observation does not influence or is not dependent upon another observation. In the case of the household model that we have taken, a household survey for example, the income expenditure model that we discussed, that I mentioned, in this case what happens that the income and consumption pattern, the relationship in income and consumption between households, for a particular household the relationship does not depend upon another household. So the relationship that we observe in the case of a particular household, suppose ith household, that is given, and the relationship in income and consumption in jth household, both are independent, they don't influence each other. We can see that is true. It is, in many cases it is realistic. In many cases the consumption pattern, it depends on certain factors like your taste, your culture, your tradition, your income level, many other things are there. So apart from income level, the other things, the excluded variable, they clubbed together in the form of epsilon I. So these things in a particular household does not depend upon the similar factors in another household. So this is a very realistic assumption at times, but there are certain other cases also. There are some exceptions, or there could be situations where these assumptions may not hold. A fourth assumption that we have is that the independent variable is not getting influenced by the error term. So xi and ei, epsilon I, both are independent. As a result, the assumption that we have is expectation of xi epsilon I is 0. So basically in this case the error term, which could be the excluded variables, which could be some random behavior on the part of households, that does not influence their income level, that influences their expenditure, but that doesn't influence their consumption. It is a fairly good assumption, fairly realistic assumption also. Now let's come to the another thing, like here how do we estimate this model? The OLS model that we have taken is yi equals alpha plus beta xi plus epsilon I. So on the basis of least squares method, we estimate these things, we estimate these equations, and like we take the method of least squares and we minimize that square of epsilon I. That means from the model we take epsilon I, square it, sum over all the observations, so that is summation epsilon I square. This is the sum of squares of the error terms. So we minimize these things. So while doing that, that means we take the partial derivatives and with respect to alpha and beta, because alpha and beta we are going to find out, we are going to estimate. So what alpha and what beta will give us the minimum values of the summation epsilon I square. So this thing that we are going to find out, and this is found out by taking the partial derivatives of this least squares and this sum of squares, error sum of squares with respect to alpha and beta. So since there are two parameters alpha and beta, we get two normal equations, and by solving these normal equations we get the estimate for beta, which we denote as beta cat. So this beta cat is the estimate of the parameter beta. In our original model, we had alpha plus beta xi. Okay, so alpha and beta are the parameters. So when we take the estimate on the basis of the sample, so this alpha cap and beta cap, this is the notation that we use. So a cap or a hat over a parameter, that means that it is an estimate obtained from the sample. So the estimate of beta cap in this case, in our model, in our OLS model, is given by the equation that you can see on the monitor. Okay, so this looks quite complex, isn't it? When you try to estimate this beta cat, you have to take summation xi, summation yi, then summation xi yi, then summation xi square, summation xi whole square. So many concepts are there. So in order to make the computation simpler, what you have is like you can take the model in deviation form. Deviation form in the sense that there are two variables xi and yi. So what I do, like I subtract x bar from xi variable. From all observation I subtract the mean. If I have 100 households as my sample, so for each household I have got the income of the household, monthly income of the household, that is my xi. So for each household I subtract the average of those 100 households. So that way I get some deviation form. I am getting the income variable in deviation form, that I denote as lowercase xi. So lowercase xi is capital case xi minus x bar. So similar for y variable also, similar for expenditure. For the 100 households, what I do, I find out the mean expenditure of those 100 households and subtract that mean expenditure from each households. So as a result I get the lowercase yi. So look, in this case the estimation of beta cap is so simple. It is given by summation xi yi by summation xi square, all lowercase. So by taking just if I prepare a table and find out the xi and yi in division forms, then I find the multiplication, the product of these two variables xi and yi, and in a third column what I do, I find out the xi square. I find out the square of the deviation of the independent variable. So it is given as beta cap is equal to summation xi yi divided by summation xi square. That is the estimate for beta. So once beta cap is estimated, once I get an estimate of beta, then the estimate of alpha is simple. I can find out the average of the sample. Y bar equals, suppose, alpha plus beta x bar. On an average that holds. So if I apply y bar, beta cap and x bar into the equation, automatically I get alpha. So that is the alpha cap. So the estimates of both the variables, both the parameters are available to us in this method. So what I do afterwards is that this estimate of these parameters, in this case by the method of least squares, is having certain properties. It is called the method of least squares because we are finding out the estimates by finding the summing over the error terms, the square of the error terms, summation epsilon I square. We are minimizing that thing. So because of that it is called least squares, and ordinary least squares because it is the simplest model, simplest linear model involving two variables only. So because of that it is called ordinary least squares or the OLS model. So in this case you can find that the beta cap is an estimate of, suppose if it is given by beta plus summation xi epsilon I by summation xi square. Because by simple manipulation, by simple operations, I can substitute the value of yi in the model and then get this equation. Similarly, the variance of beta cap is given by summation sigma epsilon square. This is the variance of the error term that we have assumed. We have assumed that it is sigma square, or you can call it sigma epsilon square. Just I put the subscript sigma here in this case to avoid the scope for confusion. And sigma epsilon square divided by sigma xi square, this is the variance of the model, variance of the parameter. So from the variance you can find the standard error by taking the positive square root. So if you are taking the positive square root of this term, this variance, in that case you get the standard error. So what happens that there are certain properties that comes up from the OLS estimation. In the OLS estimation we get the beta, the estimates which are the best linear unbiased estimate. They are called best linear unbiased estimate. We saw in the previous slide that in the previous one here that beta cap can be manipulated or can be described as beta plus summation xi epsilon I divided by summation xi square. That means beta cap is a linear combination of these things. So it is a linear estimate. Okay, it is linear in x. Then secondly, it is unbiased. That means on an average, if you take the expected value over all the samples, all possible samples, in that case you will get the population mean. So for the population parameter, whatever like parameter is, the actual value of parameter beta, that is available if we consider all the samples and take the expected value of the betas obtained in all samples. A third property that it has is it has the minimum variance. So as a result it is linear one, it is like unbiased, and third it has the minimum variance. So because of this it is called best linear unbiased estimate, or in short we call it BLUE, blue. So this beta is blue. So the estimate of beta that we obtain, beta cap, that is by through the method of least squares, that is blue. Okay, so now let's come to the topic of autocorrelation. What is the situation? What is when does autocorrelation comes up? The autocorrelation comes up when a particular assumption in the OLS model is violated. When this assumption that the expectation of EI, EJ, epsilon I, epsilon j is not equal to 0. When this assumption is not met, in that case we have the problem of autocorrelation. Means why is it called autocorrelation? It is called autocorrelation because the error terms in two observations are getting influenced by each other. So the error terms, they are not free from one to another. That means the expenditure of one household is getting influenced by the expenditure in another household, in our previous example that we have considered. So there is many times that comes up, like in order to keep pace with our neighbors, in order to compete with them, in order to follow a particular tradition, follow a particular pattern, we may be imitating one household, or there may be a very common thing also, common pattern also. So as a result, what is happening in this case, that the variables, the observations particularly, not variables, the observations, they are influenced by one another. They do not have independence. They are not independent. So the epsilon I and epsilon j, the error terms in the ith observation and the error term in jth observation, they are not independent. So when this sort of situation comes up, then we have the problem of autocorrelation. In many other models also, you can face similar situation. Like particularly what happens that in the case of time series data, the observation in a particular field, particular year, particular time period gets influenced by the previous observations. For example, there could be many situations, there could be many circumstances under which the one observation influences another observation. For example, I can show you a particular autoregressive scheme. Here, suppose epsilon t, there is a normal error term. Suppose ut is the error term for a particular equation. Suppose for a particular observation or in the regression model, you have the error term ut. So this ut is not independent of ut minus 1. There is the ut in or the error in previous time period. Here I call it ut. I use the subscript t because usually autocorrelation is found in the case of time series data. Here this is a excuse me, this is a question of first order autoregressive scheme. That means ut is dependent upon ut minus 1. So if observation is being influenced by the previous observation, what I consume this year, there is determined partly or influenced partly by what I consumed last year. What my production in my field, in my factory or in my field is determined by the production in the previous year or previous time period. So this is a situation. In fact, what happens that this is very realistic in many cases, because in cyclical behavior you might have heard in macroeconomics that many variables they move together. When the economy is passing through a boom, for example, in that case suppose your many variables they move together, or there could be suppose many econometric models where some predetermined variable, some lagged variable is used as a regressor or explanatory variable. So in this case also, like the chances of autocorrelation exist. So sorry. So when you have the situation of autoregression, like it is called autoregression because like here ut is regressed, or you are encountering a regression equation sort of situation in the case of the error term. Ut is equal to rho ut minus 1 plus epsilon t. In this case, ut is the error in the equation, and this equation, this error is influenced by the error in the previous observation, in the previous time period, and epsilon t is the normal error term that you found in the case of OLS, which fulfills all the assumptions in the OLS model. But here ut doesn't fulfill all the models. Ut is not independent of ut minus 1. So the assumption that you had in the OLS model, that expectation of epsilon I and epsilon j equals 0, that assumption is violated in this case. Here in this case, there is a relationship between ut and ut minus 1. So two observations, they are not independent. So this is the problem of autocorrelation. Autocorrelation means that the observations are correlated, and the error term, it follows a particular correlation pattern. The rho, that is the correlation ratio, in fact correlation, the degree of correlation between these two error terms, that is rho. So it is called autoregressive also. Here I have given you one example of a first order autoregressive scheme where ut depends upon ut minus 1, but you can take a higher order autoregressive schemes also. If suppose ut depends upon previous two periods, suppose whatever decision that you take, your production or consumption or any dependent variable, that suppose depends upon previous two time periods. So in this case you will have a second order autoregressive scheme, and ut will be equal to rho ut minus 1 plus rho, suppose again rho square or some other like structure that you can put, ut minus 2 plus epsilon t. So you can have a econometric model where the error terms are autocorrelated, right? So this is the situation, this is the model that we like discuss. So what happens that just because one assumption in the OLS model is violated. Just because one assumption is not fulfilled, you have a situation of autocorrelation. And what are the consequences of that autocorrelation? The consequences are that the variance of the error term sigma epsilon square, that is underestimated. The variance of the error term is less than the actual ones. So as a result, what happens that the ESS, the error sum of squares, that is lower, that is compared to the actual error terms, the impact of the error terms, that is less. That means your regression sum of squares, RSS, that is higher, because TSS, the total sum of squares, is equal to ESS, error sum of squares, plus regression sum of squares. So if your error sum of squares is less, if it is underestimated, that means your regression sum of squares is overestimated. That means the R squared, which is the coefficient of determination, that is overestimated, that is more than the actual one. So as a result, what will happen? When you have the lower value of epsilon square, sigma E square, the variance of the error term, and higher value of the R square, in that case, what could be the possibilities? In that case, what will happen? That R square, that is used to test the overall model. On the basis of F test, by using F test, you can find out the significance of all the parameters in the equation. So both alpha and beta, they can be estimated. The significance of the alpha and beta parameters can be found out by R square by taking F test. So if R square is higher, so F value will be significant. That means alpha and beta will come out to be significant statistically. So when you go for the significance test on the basis of R squared or the coefficient of determination, you find that both alpha and beta are significant, or the model is significant, the parameters are not zero. But when you go for the t test, when you test for the individual estimates, in that case, since the error variance is less, so in that case what will happen? That the standard error will be higher. The standard error will be higher, and you will have a situation of, the standard error will be less, lower, and as a result your values will be like insignificant. So what happens that you get a peculiar situation, that when taking the t test, the parameters, the estimates will not be significant, but when taking the R square values, the overall model is significant. That means, which is something contradictory. So when you encounter these sort of situations, that you have very high values of R squared, the model is explained very well, but the individual estimates are not significant, in that case this could be because of autocorrelation. So this is one very rough estimate, very crude guess, on the basis of which you can find out whether autocorrelation is present in the data or not. So what happens that in the case of autocorrelation, the usual T and F test, they are not valid. They give us ambiguous or biased results. We reject the hypothesis when it should not be, or we accept the hypothesis when it should be. So what we do, like in the case of autocorrelation, we test it properly. There is a particular test statistic that is called the Durbin-Watson test statistics. So on this basis, we can test the presence of autocorrelation, whether the particular data set has the problem of autocorrelation or not, that we can find out by the Durbin-Watson test statistic. So what happens, this Durbin-Watson test statistic, this is given by D equals summation of ut cap minus ut minus 1 cap whole square divided by summation ut square, as given on the monitor. Here see that ut cap is the estimated error term. When you estimated the regression model, and from the regression model you have the estimates of the error terms. How do you get that? Like you have, suppose alpha cap that you have got, beta cap you have got, by the OLS, and from the alpha cap and beta cap you can get yi cap, the estimated value of y on the basis of this model, the regression equation. So when you have yi cap, so if you subtract that yi cap from yi, the actual observation, you get an estimate of the error. So since the error is not observable, we cannot say with certainty that this is the amount of error that we have. The stochastic error term that we have is not estimable, it is not like it is not observable. Only we can find out some estimate of that. So what happens that in this case the ut cap, this is the estimate of the error terms. So based on our OLS equation, based on our OLS model, we can estimate the error terms, and that is the ut cap. So from the ut cap, given this equation, as you can see on the monitor, you can find out the value of d, which is the Durbin-Watson statistic. So by interpreting this d, you can find out whether a particular model has autocorrelation or not. One interesting thing is that when we take d for large samples, this tends to a particular value, that is 2 into 1 minus rho. So whatever is the autocorrelation in the model, whatever is the autocorrelation between error terms, that is rho. Okay, and we have to estimate this rho cap. We have to find out some estimate of that. So in the model, that the autocorrelation, if it is rho, then the d statistic will tend toward 2 into 1 minus rho. That means if rho is 0, if in a particular situation, in a particular model, for a particular data set, if rho is equal to 0, in that case it will tend towards 2. So this d, or the Durbin-Watson statistic, tends towards 2 when there is no autocorrelation at all in the model. But if there is autocorrelation in the model, then what will happen? It will deviate from 2. It could be either less than 2 or it could be more than 2 also. So 2 is the case, 2 is the situation when the d, or the DW statistic, which is d, estimated as given in the monitor, which if it is around 2, in that case there is no autocorrelation in the model or in the data set. But if it is different, then how do we find out whether a significant autocorrelation is present or not? How do we reject a hypothesis that this data contains autocorrelation or not? The d statistic depends upon the variable, the number of explanatory variables. So according to the number of explanatory variable, it depends what is the value of the d statistic, and according to the number of observation also it varies. So what happens that it is very like complex to memorize all these things or to estimate all these things. So there is a particular table which is called the statistic for DW statistics. The table for DW statistics that is available in most of the econometrics model, econometrics textbooks, or it is available on the website also. There are many websites which offer you the tabulated value of this DW statistics. You can check there, and these are all given in the form of a particular table. So in the table, what happens that the usual variable, the usual value of the d statistics should be equal to 2. In the case when there is no autocorrelation in the model, in that case it should approach 2. If it is less than 2, in that case there is autocorrelation. If it is higher than 2, if it is greater than 2, in that case there is autocorrelation. Okay. So then we have two limits, the upper limit and the lower limit. So depending upon these two limits, what is the lower limit and the upper limit? So depending upon these two limits, we can decide whether the hypothesis should be rejected or not rejected. What happens that in the case, suppose like we have a situation like if it is reject the hypothesis, if it is less than the lower limit, or higher than the 4 minus dl. This is the condition. If your d statistic that you obtain from the model by estimating from as given in the previous equation, in fact, that I showed you how to estimate d, how to find out d. So if the obtained value of d is less than the dl, the tabulated value of the lower limit, or if it is greater than the 4 minus dl, in that case you reject the null hypothesis. That means there is autocorrelation in the model. If suppose if it is towards the value 2, in that case there is no autocorrelation and the hypothesis is accepted, or the hypothesis is not rejected. Okay, so this is how the test for autocorrelation can be undertaken. And how to, suppose the next stage is, suppose you found that there is autocorrelation in the model, then what will happen? Then there are certain mechanism, there are certain techniques on the basis of which you can find out how to solve for the problem of autocorrelation. So there are three methods particularly that you will find, and these three methods are the Cochran-Orcutt method, Hildreth-Liu procedure, and Prage-Weston procedure. The details about these procedures, these methods, are given in the textbooks, in the block that you are supplied with. In block 2 of the econometrics methods course, in this course, the block 2 particularly, while dealing with this course material, we have given the procedure of how to implement these tests. So these tests, Cochran-Orcutt method, Hildreth-Liu procedure, and Prage-Weston procedure, these three procedures particularly that you can utilize, that you can find out. Okay, so this is how the corrections for autocorrelation is there. Thus we discussed that what is the problem of autocorrelation, when certain assumptions in the OLS model is violated, then we get the problem of autocorrelation. Then we discussed how it is detected, particularly by certain features. When you have a very high R-square value and low T value, then you can judge, you can find out that there could be the possibility of autocorrelation. Then we gave a particular test statistic, particularly the Durbin-Watson test statistic, through which you can test the presence of autocorrelation. Then we suggested some remedial measures, some procedures, some methods, how to rectify the presence of autocorrelation. In the presence of autocorrelation, since the OLS estimate is not blue, the OLS, ordinary least square method, does not apply. It is not the blue, it is not the best method in fact. So we have to find out some other method to estimate the model, and these methods could be Cochran-Orcutt method, Hildreth-Liu procedure, and Prage-Weston procedure. So these are the three methods that we have discussed in the block, and you can find out. Next come to the problem of heteroscedasticity. Heteroscedasticity is because of the violation of another assumption in the OLS model. The second assumption in the OLS model that we saw earlier is expectation of E square is equal to sigma square. It means that the variance of the error term is constant throughout the model. That means the variance does not change from observation to observation. For example, for a concrete example, suppose for the question of the households, in the example of the households regarding income and expenditure that we discussed earlier, in this case the variance in expenditure of the lower income groups, the poorer households, is same as the variance of the richer households. Okay, so this is when this situation, when the assumption, the OLS assumption that expectation of epsilon square is equal to sigma is violated, when the situation that we encounter is expectation of epsilon square is not equal to sigma square, when the variance of the error term is not constant, it changes according to observations, then we have the problem of heteroscedasticity. So what are the consequences? What happens when we have the problem of heteroscedasticity? In this case, again, the estimate of beta is unbiased. The beta, if we estimate the OLS model in the presence of heteroscedasticity, in that case still we get unbiased estimates of beta. That is true of the autocorrelation problem also. In the case of autocorrelation also we found that the beta is unbiased, but it is not efficient. So similarly in the case of heteroscedasticity also, like it does not have the minimum variance, so thus the beta estimates are not blue. They are not the best linear unbiased estimates. They are linear, they are like in the case of heteroscedasticity, even it is not linear, as you will find that the variance is not minimum and it has many other terms apart from the variance of the beta that we found earlier. So it is not blue, it is not the best estimate that we have. So in order to test the presence of heteroscedasticity, what do? We have many test procedures, in fact, particularly 3 that we have discussed in the block. One is White's test. This is the method suggested by White. Then there is another, this Goldfeld quant test. This is the second method that we have discussed. And there is a third one, this Broyes-Pogan test, so which is suggested again by Broyes and Pogan. So these test procedures are according to the economist or the econometrician who suggested these methods. So these are the 3 methods that we have discussed. Okay, so by taking these things into account, you can find out the method. So in this model that we discussed today, the presence in this session we discussed the problem of autocorrelation and heteroscedasticity, and we discussed how they occur, in what situations, what circumstances these 2 problems come up in the econometric models, and we dealt how these problems can be tackled and what are the procedures to estimate given the problems of autocorrelation and heteroscedasticity. So we'll take up some other issues in the next session. Till then, goodbye. Thank you.